Okay, this is a Northmont answer key, and you see the answers are already here, so that makes my life easier. Number one, of the following compounds, which is the most ionic? Well, there's only one ionic compound in the list. Those are all covalent compounds, so it's got to be this one. Number two, which of the following oxides is a gas? Well, rubidium oxide is an ionic compound. Ionic compounds have very strong intermolecular forces of attraction. So same with sodium iodide, so with this lanthanum. Okay, so those are ionic. Silicon dioxide is a covalent network solid. That's like quartz crystal. So the one that's a gas is the one that has the lowest number or the smallest intermolecular forces of attraction. So that's got to be N2O. Okay, the elements of which of the following have nearly the same atomic radius? Okay, you're going to have nearly the same atomic radius, of course, if you're within the same row. But within the same row, if you're within the same orbital, you're going to win. Going up and down, you're not even in the game because you change energy levels. So when I look at these quickly, it can't be D because that's going up and down. It can't be B because that goes up and down. And so now you have the choice of A or C. If you look at A, we're going from beryllium, who is an S, to the p orbitals. And these guys are all, under C, are all in the d orbital. So they're the winners. Number 4, which of the following pure substances, of them, which has the highest melting point temperature? Well, it's the covalent network solid, silicon dioxide. Why do I know that's the answer? Well, this guy in letter E is nonpolar. It's nonpolar covalent. That's going to be held together only by London dispersion forces. Okay, same with, well, I guess same with all of them. And then London dispersion forces would increase with the molecular weight, which would make iodine have a pretty high one, but you need to know silicon dioxide is a covalent network solid. All right, I think we have C on this one. Ionization energies. Without even looking at the question, when I look at these ionization energies, that's the energy it takes to steal somebody's electron. So it's okay to take the first one. It's okay to take the second one. It's okay to take the third one. But you ain't ever going to take this fourth electron away from this person. So what that means to me is this guy is going to be +3. He'll easily lose 3 electrons, but you're not going to take the fourth one away. Now, the question says, who is it? Well, sodium's +1, magnesium's +2, aluminum's +3. So there we go. These guys are going to be negative. Okay, where are we at? Number 6. Which one is isoelectronic? In order of increasing radii. Isoelectronic means same electron configuration. So you have to decide that one first, and then in order of increasing one. So if you look at oxide and fluoride, they're the same as neon, right? And then the sodium ion and the magnesium ion. These guys right here are isoelectronic. Magnesium is not bigger than sodium. Well, nope, he's not bigger than sodium. If you're looking at the bottom row, the magnesium ion and the sodium ion, okay, that's good. And then neon, the fluoride ion, the oxide ion, that's good. The -2 is bigger than the -1. And then you've got the +1 and the +2. Remember, the more positive the charge, the more that it sucks in the electrons, it's going to make a smaller ion. Okay, number 7. Which of the following represents the ionization energy? Ionization energy is the energy required to rip off an electron. And so here, this is the answer because it's 1 I and you've got 1 electron. Okay, given these 3 statements, pick the best answer. Beryllium is larger than lithium. That ain't right. The beryllium ion is larger than the lithium. That ain't right. The chloride ion is larger than the sulfide ion. That is way wrong. So I would say all three are false. Okay. Okay, so now we have a pKa curve. And when I look at this curve without even looking at any of the writing, what I see first and foremost is we're starting here. That means it's a weak acid. If it were a strong acid, you'd start down here by 0. Also, I know we're titrating with a strong base because we're ending up closer to 14. Points that you need to know on this graph is halfway up this hill, right here, is the end point. And that's the point where the number of moles of acid used will equal the number of moles of hydroxide. The other point you need to know is right here, which is halfway to the end point. This is the point where pH equals pKa for the acid. And the reason pH equals pKa for the acid is because if this is your Henderson-Hasselbalch equation, when you get to the point where the base and the acid are equal, then the log of 1, this is 1, so the log of 1 is 0. So when the base and the acid are equal, the pH equals pKa. That happens halfway here, because at the beginning you have all HA. When you've used up half of it, you have half HA and half sodium hydroxide. Okay, let's look at the questions. What's the concentration when you begin? Well, here's a pH. The pH when you begin is 3. If the pH is 3, the hydrogen ion concentration is 0.001. That was a no-brainer. All in nerdlings. Okay, how many milliliters of base was needed to neutralize the unknown monoprotic acid? Well, the end point of the titration is here. So the number of milliliters there is in the 20s. Whoops, wrong way. One more. So it's 28. That's good. Using the graph, calculate the approximate Ka for the unknown acid. This is from that point on the graph where pH equals pKa. So the pH here is 4 point something. It's almost 5 if you take this line straight over. That's going to be the pKa of the acid, which is 4.8. Is that not a multiple choice? All right. Based on the information below, what would you guess the identity? Well, if the pKa is 4.8, then the Ka equals times 10 to the negative 4.8, which would be something times 10 to the negative fifth. Now, it's a crapshoot, like whether it's which one of these. So you could use your calculator, or you can use those great math skills that Mr. Skilton has given you. He's a teacher, right? Just kidding. Okay, for this titration, which indicator listed below would you think would be best suited? Okay, so the indicator's just a weak acid. So the pH at the end point should come close to the pKa for the indicator. Now this one just gives you the pH ranges for the endpoint, so that was just a dumb question. So at the endpoint, if you extrapolate this over, the pH is around 8. So I'm going to be choosing this guy right here. Look at that. Okay. Okay, so now the fun begins. And we have an equilibrium constant question. This is great. This is the lab we're going to do in 2 weeks. This is fun. So you've got the iron and you've got the SCN. You put them together and you get blood red. The cool thing about equilibrium is that if you start with 25 irons and 12 SCNs and none of those guys, These guys are going to react, right? You're going to use up some of these. Let's say we use up 10 here, and you would make 10, right? And then at the end of the game, you're going to have leftovers. So let's make that line a little bit higher. Okay, so you start with 25, you start with 12, none of that. 10 of these guys react, so you're going to actually add 10 over here. And so now at the end, we have 13 of these left over, 2, and we have 10. Or you could do it again with a different amount and say you've got 12 here, 8 here, 0 here, and 5 of these react, plus 5 here, and you have leftovers. Okay, equilibrium constant is a constant. It means that at the end of the game, the concentration of FeSCN over the iron times SCN is a constant. So the ratio of FeSCN over this times this will be the exact same, regardless of the amounts of these guys that you use. So when you do this lab, it's important to remember, okay, to do this, do the table in moles. Then, before you put it into the equilibrium expression, change it back to molarity. Because you have to be in molarity in order to be using the equilibrium expression. So, if you have 5 milliliters of a certain concentration, change it, figure out how many moles you're using here. And if you have 3 milliliters, figure out how many moles you're using here. And this one would be 0. Then you put the stuff into spec 20, you use the graph, you find the concentration of this that you make at the end, change that to moles, and then do your math. Okay, so that's it for now, and I will finish this in a little while.